Okay, hello everyone. My name is Felipe Verástegui, and thanks for being here. I'll tell you a little bit more about this work titled An Adaptive Robust Optimization Model for Power Systems Planning with Operational Uncertainty. So the background for this work is basically the generation and transmission EP problem. And this is an important problem as it allows us to gain insight on the long-term development of power systems and how they may integrate large shares of variable renewable energy. So while modeling the operational part of these highly renewable future power systems, of course, several challenges arise. On one hand, there's the modeling of uncertainty, where there are techniques such as stochastic programming and robust optimization. And on the other hand, there's the modeling of variability, where early concepts such as the load duration curve and load blocks have evolved into new methods such as representative blocks or representative days in recent models, which basically try to preserve to some extent the chronology of the operation, enabling the inclusion of key flexibility constraints without comprising too much computational tractability. And even though representative days do capture to some extent the variability and some of the operational uncertainty of a highly renewable power system through a stochastic-like structure, there is a large amount of operational uncertainty which is not considered in these modeling structures. And this is why many EP models include additional parameters and additional constraints to protect from operational risk, such as planning reserve margins. So here we ask ourselves, is there any better way to do this? And this leads me to the contributions of this work, where we're basically proposing a novel two-stage adaptive robust optimization model for the EP problem based on the idea of using uncertainty sets from robust optimization within these representative days. And so to explain this, suppose you have a cluster of operational data, say a cluster of load profiles, and you want to represent this data on a planning context. So you can either choose a representative profile and protect against operational risk through a planning reserve margin, or alternatively, you could build an uncertainty set around this representative profile, and then you can protect against uncertainty through the size of this uncertainty set, which can be controlled by a single parameter we'll call from now on gamma. And we also want to provide some experimental evidence of how these approaches would work. So we'll call one DEP and the other one REP. And let me show you some results really quickly. So we applied these models to a scaled version of the Chilean power system over a planning horizon of 20 years. And basically we solved 4 instances of each model, which are basically 4 different levels of conservativeness. So first we took a look at the results from DEP. And for instance, if we take a look at new capacity, which is here plotted geographically, so at the left you have the far north of the power system and at the right you have the far south. And if you compare a non-conservative solution with a conservative solution, say for instance a higher planning reserve margin, you'll see that the main difference is that in the second solution, DEP meets capacity requirements in a cost-efficient way, but does not change any of the prior investments, say for instance in renewable generation capacity. On the other hand, if you take a look at REP and if you compare a non-conservative solution with a conservative solution, you'll see that it penalizes variability and it also diversifies the risk of having all PV installed in a single location. So there's a sort of statistical and spatial intelligence to the REP model. And this of course comes at a computational cost. In our case, REP took about 10 hours in solving this case study, while DEP only took minutes. And we did some more experiments on this. You can check them out in the paper. Actually, REP does not scale that bad. And another thing we wanted to look at is how would the expansion plans from each approach perform in an operational context. So we set up a simulation where we solved around 2,000 daily operational problems through the planning horizon as to estimate the expected cost from operations. And then we took a look at total cost over the planning horizon. So here you're seeing the investment plus operational cost from the simulation for DEP and REP. And we're plotting solutions by conservatism level. So at the left, you have the less conservative solution, and at the right, you have the most conservative solution. And then you can see that the best solution from REP outperforms in this metric the best solution from DEP. And if you take a look at another metric, say for instance, load shedding, you'll see that the best solution from REP also outperforms the best solution from DEP, both in terms of frequency and total load shedding. So basically the REP expansion plans are finding a better way of performing in operations and with a lesser total cost. And this is sort of a expected value result from the operation based on the simulation. But you can also take a look at the worst days, for instance, say the max daily cost or the average of the 36 more expensive days. And you'll see once again that the best solution from REP outperforms the best solution from DEP. So basically the REP model is finding a better way of preparing against operational uncertainty and variability through this statistical and spatial intelligence. And there are more discussion about this in the paper, but basically we have developed an adaptive robust optimization model with an effective representation of the operational uncertainty and variability through the use of these uncertain representative days, which provide the spatial and statistical intelligence in resource placement. And of course, this pays off in both cost efficiency and reliability in the operations. So I hope you enjoyed the presentation. If you have any doubts, you can contact me, and have a nice conference.